This drives me crazy. Amazon has not gone back to the monolith. If you could add characteristics a la carte, then every system would be ultra performant and ultra scalable. As an architect, you should repeat yourself early and often to anybody that can listen.
So right now, next to the computer science education, you need a degree in physics.
Well, doesn't hurt.
And today we're discussing like multiple things. A lot of them will be based on your book called Software Architecture, The Hard Parts.
Yep.
As I remember, it is a continuation of another of your books called Software Architecture.
Fundamentals of Software Architecture.
Fundamentals of Software Architecture.
Right, exactly. Which came out in a second edition. We actually tell people that the Hard Parts book came about because as we were writing the Fundamentals book, we kept bumping into problems that were too deep and too difficult to go into a Fundamentals book. And so we set them aside into this pile that got bigger. And at one point on the endless phone calls that Mark and I had, he suggested, as we were ejecting yet another perfectly good example for being too complicated, he said, maybe we should call our next book The Hard Parts. And that's exactly where the title of the book
Okay.
It was the collection of all those things.
All right, so this is where the book originated.
Exactly, yeah.
Yeah, it's actually pretty hard because you bring pretty fundamental and profound problems that need to be solved. And I hope this is what our conversation will be about today. One of the first things that I bumped into is you mentioning the architecture trade-off analysis method, like in one of the first chapters. And that's a pretty formal method, right? So it requires particular steps, a lot of stakeholders, and analysis procedure. But I find this pretty formal and expensive.
Which is why we tell you don't do it. That's our advice about it, is don't. It makes no sense in the current day and age. I mean, when you think about when ATAM, you're talking about ATAM, the architecture trade-off from SEI. When it was originated, it made sense because IT moved very slowly at that time. And it was reasonable to say, let's get every single interested person in this piece of software in a room together for a week-long meeting. Yeah, good luck doing that in the current day and age. And then what would the output of that be that wouldn't be irrelevant in a week? The ecosystem has completely overcome the old ways of doing trade-off analysis, which is why we focus so much in the Hard Parts book about what are the modern ways to do this, the ones that you can get instant feedback with, not 100 meetings.
So is the main disadvantage is cost and velocity? Anything else?
Bureaucracy. So one of our sort of sub-goals in a lot of our writing, including the book we're working on now, which is going to be in many ways the completion of kind of a poorly named trilogy of books, is getting fast feedback on things that are important in software. And a lot of formal trade-off analysis techniques like CBAM or HAM or all of those, in our opinion, try to create artificial bureaucracies in place of feedback loops. And we'd much rather have actual feedback loops based on real facts than these kind of artificial checkpoints and bureaucracies. Now, a lot of those things are necessary when you couldn't build automated feedback loops, just like it was very necessary before we could automate machine creation. It was necessary to have a platoon of people running around installing software updates to servers and missing a few, and one of them but that was the only option you had. But over time, we learned how to automate that and get faster feedback and more effective change through automation. And that's what trade-off analysis has to be now. It has to have a faster feedback loop then. Let's have a meeting and then digest for 4 months.
But how it should look like you're saying fast feedback loop, but does that mean that you need to actually go and implement some solutions and then
so you mentioned the first chapter of our book, the last chapter of our book. So there's a weird side effect of writing a book during a pandemic, which the Hard Parts was written during the pandemic, is there are a lot of Easter eggs scattered throughout the text in the Hard Parts book that nobody's found all of them because some of them are pretty obscure. But one of the sort of interesting little things that we did, and I'll tell you another one in just a second that is the most humorous of them. But one of the things that we did is the first 14 chapters of the book are written in either first or third person. So it's the royal we as the authors, or we're talking in the third person. But the last chapter of the book, we switched to second person. And that chapter is called Build Your Own Trade-Off Analysis. And we address the reader directly in that chapter because what we've been doing throughout the entire book is showing you how we're applying these different kinds of trade-off analyses. In the last chapter, we show you how to build the same kind of trade-off analyses that we've been utilizing throughout the book to illustrate all these points along the way.
Okay. Yeah, that's definitely true. Yeah, I'm going through it exactly. So coupling, qualitative versus quantitative analysis, and so on.
And that's the one that answers your question. So one of the tips that we give there is, so what you're talking about is building stuff and actually measuring it. Nothing beats, that's the best possible feedback you can get. But here's the problem. There are 8 possible ways to implement this transactional saga workflow. So one of the ways you could do this is go to your boss and say, boss, I have good news and I have bad news. The good news is I'm going to give you the objectively perfect workflow for the new accounting system that we're building. I can prove that it is the best possible one. The downside is it's going to take me 8 times longer than you'd expected and 8 times the budget, because I'm going to implement all 8 of them, measure them all, and throw away the 7 that are not as good as the last one. If you can do that, you're guaranteed to get perfect stuff. But nobody can do that. And so what we talk about is qualitative versus quantitative analysis. Qualitative analysis is applying the qualities of something without necessarily measuring it. So we do this a lot. So in our fundamentals book, we compared all the different architecture styles. So when you look at architecture styles, those are the named topologies in architecture. They're all generic, meaning that you can implement pretty much any behavior in any architecture style. The way they really differ is how they support different capabilities, like scalability versus responsiveness versus security, etc. And so that's how we compared those styles, is we created these star chart ratings of, okay, modular monolith, how much more scalable or less scalable is this than microservices? Now, I don't know for all time, but we have this 5-star rating. And so a modular monolith would get 2 stars and microservices would get 5. I don't know exactly how much more, but by understanding the nature of what makes things scalable, what creates limits on scalability, I can assign qualitative values for those. And that's a way to do analysis before you've built anything, to narrow the possibilities down to a small enough number where you can start doing actual quantitative analysis on them. And that's a good example of a modern way to do trade-off analysis versus let's get together and have a JAD meeting with everybody in the company and talk about this. Here's a concrete feedback-driven way of doing that kind of analysis where you can get to the point where you can actually build something and measure it directly.
Yeah. Do I get the idea right? Is that having those stars rating for different styles according to the different characteristic to different non-functional requirements of our particular problem, then we can evaluate that if we combine it somehow by multiplication or weighted sum or something, then we can say, okay, this style is much, much better than this style for our problem.
I wouldn't say you can do math with it, but it does give you a good feel for one of the most important things, because you can really only primarily support a handful of characteristics in an architecture. You can't just add them a la carte. If you could add characteristics a la carte, then every system would be ultra performant and ultra scalable and ultra elastic and ultra secure and ultra all the things. Because why wouldn't you do that if you can just add them when you want to? They all trade off and fuss with each other. And so your goal as an architect are, what are the 3 or 4 that absolutely have to be there, the capabilities that have to be there to be successful, and then we'll figure out how to deal with all the rest of the shortcomings that come up.
But that sets the question about what are actually important characteristics for my case. So we need to understand.
And that depends on your case entirely. In fact, you'll notice the very first part of that last chapter in the Hard Parts book talks about making trade-off analysis within context. Here's the things that we realize. So you'll notice, you may have noticed already in the Hard Parts book, there's a narrative that goes along with it called the SysOps Squad, where all these people are having conversations about things. Because what Mark and I realized, so the book is fundamentally about trade-off analysis in software architecture. But generic trade-off analysis in software architecture is boring because it's mostly meaningless, because it only gets you to things that are obviously good or bad. In the real world, trade-off analysis are against concrete things where some are good and some are bad, and you have to do concrete trade-off analysis. That's why the SysOps Squad exists, is because we talk about the trade-off analysis in the generic, but then we apply it to a concrete problem to show that to do actual trade-off analysis, you need a problem, because doing it in the abstract, only obvious solutions come out when you do it in the abstract. So this SysOps squad, let me do the one other Easter egg that's funny before we continue, just before I forget about it. So you may notice in the SysOps squad, so this is just something that Mark and I decided to do as part of a sort of pandemic project. We wanted to see if traditionally technical books, when they use gendered pronouns, it's always he, just because that's the normal way that language worked for a few centuries. We wanted to see if you could write a technical book that had no gendered pronouns or no gender identification whatsoever in it. So we actually wrote a scanner that scanned all of our text as we were writing it, looking for gendered pronouns. And you'll also notice that all the names of the characters in the book are gender neutral. There's not a single gendered name in the entire book. And we wanted to see if you could write a book like that didn't read weird and seem awkward. And it doesn't. It reads like a regular book, but you can scan it and there's not a single one. I did just the other day, just for fun again to see. Yeah. But here's the funny side note about that. So that has really nothing to do with the technical content. The first review we got on Amazon for this book said basically, love the book, 5 stars, great content. The only thing I didn't like about the book was the one character I didn't like was a woman. And we have no idea who this person is talking about. It has to be a man, I'm guessing. And he identified the one annoying character as being female when there's absolutely no marker whatsoever anywhere in the text or anywhere that would identify any character as that. So it's like almost punishment for trying to do something interesting. The first review comes out and points out something. It's like, we still don't know who this person's talking about, because to us, none of the characters are any more annoying than any of the others. So we have no idea. So that's
how have you felt about this review?
For things like that, you have to do Olympic reviewing. You throw out the best ones and the worst ones and just take the average.
Okay.
Because there are always trolls, and
makes sense.
You can't control how people react to what you do out in the world. So
I need to agree that the whole narrative reads pretty natural, right? So you don't bump into what the hell and so on. Yeah,
actually, I want to also Mark's wife is a novelist, and she actually reviewed a bunch of our dialogue to improve it significantly. So it would have been a lot worse if she hadn't looked at it and helped us out, because we've never written dialogue before. So that was another challenge as we were writing the book, is to actually create convincing conversations between people.
How have you approached writing the book? Have you laid out the technicalities first and then put the story upon it? Or you came up with a story first and then added the technical content? Or it was a mixture of both?
It's a great question. A question that doesn't come up as much as you might think. And actually, Mark and I have, in my opinion, innovative in the way that you write technical books. And this goes back to what I was talking about before, which is fast feedback. So generally, when you write a technical book, what you do is you come up with a good idea and you go lock yourself into a room like this for weeks and months and never see sunshine and struggle over it. And maybe you do one early release and you finally release the thing. But the problem with that is terrible feedback, no feedback loop. And so what Mark and I do, actually I started this before Mark and I started the Fundamentals book. The first book I did this on was Building Evolutionary Architectures, where we had a seed of an idea, and so we started talking about it at conferences. We started doing workshops. We did an hour-long workshop, and then a half-day workshop, and then a full-day workshop, and then a 2-day workshop, and it iterated on the material. Because what we're doing is every time we present the material, part of the goal is I'm going to make this material substantively better in at least one way for the next time I present it. And that does two things. One, it keeps you constantly on the lookout for how can I make what I'm presenting better. And because you're putting effort into making it better, you want to try to do it again because you don't want to waste the effort you put into making it better. And so we iterate on the material like that. And so that's exactly what we did with the Hard Parts book. We started teaching workshops. And in fact, the workshops were derived from the most difficult problems from the Fundamentals workshop that we did. We extracted those and built more complex exercises. And we realized, as part of the workshop, we have to have context for these trade-off analysis. That's where the SysOps squad came from, was the workshop. As we started writing the book, we started trying to write the book without the SysOps squad, and we realized the problem I was talking about before of lack of concrete trade-off analysis, and that's when they crept their way into the book. And so while we were doing the workshops, the SysOps squad was actually our exposition examples and the basis for all the exercises the students were doing. But what that allowed us to do is iterate on those examples and tweak them and change them and make them better, much more illustrative of the core problem we were trying to get at. And it also allowed us to actually get to the core problem, that the real underlying trade-off analysis, because the more you talk about it, the more insight you get into it, and the deeper you can get into seeing, okay, what is the actual crunchy center here that's driving this trade-off analysis? So that, and we're doing the exact same thing right now on our upcoming book, which is called Architecture as Code. We just finished teaching a whole series of hands-on workshops based on that material, and we're starting to write that book now. I'm surprised, and in fact, a lot of my colleagues are now writing books iteratively like this. I'm surprised that more people don't write books iteratively like this. It's not a waterfall kind of a process. You got to have, when you're writing a book, you're by definition going somewhere that nobody's been before. And anytime you're taking a trip like that, you need fast feedback to make sure you're not wandering off the path. And so that's a way to iterate on IP without the very long, cumbersome stage of writing it down, because writing it in prose is the slowest feedback loop. And so doing it through conferences and training classes allows you to iterate much more quickly.
What were the most impactful realization from this feedback loop? What made you change the book significantly?
No question about it. We easily point to a major revelation in the Hard Parts book. And in fact, it's one of those things that came frighteningly late in the process, because if you fundamentally look at the book from a 20,000 meter view, the first half of the book is about, so we talk about a coupling in software architecture. And most people just use one term, coupling. But we differentiate in this book two kinds: static coupling, which are how things depend on each other and wired together, and dynamic coupling, which is what happens when you have these things start calling one another in distributed architecture. So that's part one, part two of the book. That, by the way, was an arbitrary split between those two things into part one and part two. And we did that split and then wrote the book. And then when the thing was finally done, we went back and looked, and out of 450 pages, part two starts on page like 220. So it was almost exactly halfway in the middle of the book. But the second half of the book is by far the most complicated stuff, which is how do you do trade-off analysis for synchronous versus asynchronous communication, and orchestration versus choreography, and eventual consistency versus atomicity, etc. And Chris Richardson, in his Microservice Patterns book, wrote about sagas, orchestrated and choreographed sagas, but we wanted to be able to do a deeper analysis than just that. And so very late in the process, we actually realized, and this is really the heart of the second part of the book, that the reason that, and it was because of, so we were doing exactly what we do when we're trying to understand some sort of trade-off analysis. We were building a lot of examples, and then we would tweak one of those three forces that I talked about, and the trade-offs would shift dramatically from a very small change. You change from synchronous to asynchronous, and things change really abruptly. And we ultimately realized that it's because those three things form a three-dimensional conjoined space. We call those the primal forces in distributed architecture. It's communication, which is synchronous versus asynchronous, consistency, which is atomic versus eventual, and coordination, which is orchestration versus choreography. When you have a transactional workflow, changing from synchronous to asynchronous changes the trade-offs for the other two as well, because it's a three-dimensional conjoined space. And that was our revelation. And based on that, what we did was say, okay, there are three binaries basically. That means 8 possible combinations. Let's model all 8 of them, and probably half of them will fall away as being ridiculous combinations that you'd never see, and that'll give us some insight into the other ones. And that didn't happen. All 8 of them are legitimate patterns or anti-patterns that you see in the wild. There's one that's a little bit unusual, which is what we call time travel, which is synchronous communication and choreography, which is a little bit odd. But the rest of them are perfectly legitimate. And by doing that trade-off analysis, by building each one and then doing that kind of qualitative analysis, again, we did qualitative analysis, that gives you a really good feel for, okay, if I need really high responsiveness out of my workflow, what's the best combination of those three forces that I can choose that maximizes responsiveness, maybe at the expense of scalability. In this particular situation, I need responsive security. And so it gives you a way of doing a qualitative analysis across those things. And that kind of meta-analysis enables you to do that, which you couldn't have done before. So that was by far the biggest revelation in the book. And like I say, that actually happened. We literally had 2 chapters left to write, and one of them was the transactional sagas chapter. And so it came really late, but I was glad that the revelation came about. And it was literally because the revelation actually hit me because Mark and I were teaching this hard parts material probably for the 51st time online to a group of people, and I was listening to Mark talk about orchestration versus choreography, and that's when it struck me that, in fact, the image of a 3-dimensional graph struck me, and that was where that revelation came from. So it purely came from just iterating on the idea over and over. Let me give you one more example of how over a long period of time leads to a better revelation. Since time began for me and Mark, that's probably 2015 or so, we've been referring to non-functional requirements as architecture characteristics. There's an interesting history of non-functional requirements and why we don't like that term, but we've been calling them architecture characteristics forever. So our first edition of the fundamentals book and the second edition calls them that. But then we were working on head-first software architecture with Raju Gandhi. And we realized in writing that book that we probably should have been calling them capabilities all along, not characteristics, because that's where the ility thing comes from, because they're describing capabilities of the system. And in fact, in the head-first software architecture, we split design into behavior, which is the motivation for writing the piece of software, and then analyzing what capabilities it needs to support to be successful. That's a really useful split between domain, architecture characteristics, behavior versus capabilities. But the capabilities thing didn't come to us until we'd been talking about architecture characteristics for a decade. I actually pitched to the co-authors in the Head First book, very late in the process. I'm notorious for doing things late or just in time. I pitched very late in the process that we should go through and change it to capabilities everywhere, and I got resoundingly voted down because most of what we write in is the O'Reilly writing platform, which is called Atlas, which is all based on ASCII doc, which is brilliant. It's such a pleasure to write in ASCII doc for technical books, but Head First books are not. They are written in Adobe InDesign. Every single page is a unique graphic layout, and changing architecture characteristics to architecture capabilities throughout the entire book would mean that probably 75 pages would have to be completely redesigned and laid out, and I got resoundingly voted no for doing that, and that was the right call because there was no way we were going to do that late in the process.
All right, so it looks like the revelations come after a lot of work, and then you kind of get this insight that, hey, here you are.
Feedback.
Yeah, feedback loop. It's the same way in the software, right?
Absolutely.
So as much feedback you receive, the better your system get a chance to become.
So I'll give you the entire secret of my success as a consultant for these 20 years or so now. This probably covers 80% of the success I have as a consultant. When you show up somewhere, where's the feedback loop and how can we make it faster?
Yeah,
that's
exactly.
The whole thing. There's a lot of details around that, but fundamentally, you'll make the ecosystem a better place if you can say, where's the feedback loop and how can we make it faster or better?
Okay, so does it mean that the time to market is essentially the biggest characteristic of business, like from software perspective?
It completely depends on what kind of business you're in. If you're in a fast-moving startup or something like that, time to market's critical. But if you're in a high-volume finance kind of situation, my co-author Rebecca Parsons talks about a trading system she worked on where normally you think of trading systems as being super fast and low latency. This didn't have latency requirements at all because every trade was worth several $1 billion because they were trading these massive commodities. Time to market meant nothing to them. Data integrity meant everything to them, and security. And so it really just depends on the context. So what you're talking about, though, is a common goal for a lot of systems now because they find themselves in ecosystems where their competitors are moving fast. And so it's a common driver, but it's even so, we've actually played this game of, is there any architecture characteristic that absolutely has to be present in every system you design? And the one that we could come up with was security, but then Rebecca brings up the point of she used to work in the London ThoughtWorks office, and because there's a lot of traffic around there, they had a sandwich ordering app in the office that you could put in an order for a sandwich, and if it got in by 11, they would deliver a sandwich to you. They didn't need security for that because the worst thing that could happen is they'd find out that you liked egg salad sandwiches. So again, you can't universally apply anything to any system.
Well, I can imagine you can figure out if you're allergic to something and you like avoid something, and then
But it's never a bad idea.
Derive anything from that, yeah. No, okay.
It's not a critical
But
idea.
I would like to get back to this three-dimensional space. So do you say that you can start designing your system, like basically when you understand what you need, then you need to pick a choice out of those 8 options?
Yeah, or a couple of them. It gives you a shorthand way of avoiding the problem I talked about earlier. Oh, let's build the accounting workflow 8 different ways and measure it. Nobody's got time to do that. So how do you make decisions in that space if you don't have time to build a bunch of them? You can kind of guess, and you can go by philosophy, but one of the things that analysis shows, so one of the common bits of advice that you get in microservices is orchestration's not great. A choreography gives you much better responsiveness, but it turns out that's not true because some of our orchestrated workflows are quite responsive. It turns out it's the combination of orchestration and atomicity that really hurts responsiveness. So understanding how these things interact with each other helps you make more informed choices for starting to build something. That's something
so if you can ditch atomicity, then you will have much better responsiveness. And then you as architect, you need to realize this, right? So you can trade this off.
And this is the common advice you hear in microservices is don't do transactions across service boundaries and use eventual consistency. And part of the reason for that advice is because it shifts a lot of the negative trade-offs in your favor. Like responsiveness and scalability is better, and so it affects a lot of those kind of meta characteristics of architecture. What we did was analyze that. So one of the things that we did that was interesting, once we did all the qualitative trade-off analysis, Mark did a little experiment where he said, okay, as you shift from one of these styles to another, what's the magnitude of change in the star ratings between those changes? And he pitched those against the 3 forces to see which one of them has the most impact. So in other words, of the 3, if I had to choose one, which one has the most dramatic impact? And by far, it was consistency, which is exactly why you hear the advice, prefer eventual consistency in microservices. Because moving from atomic to eventual consistency makes almost everything much better. But we actually quantified that advice. So there's a lot of advice in software architecture where it's based on philosophy or rule of thumb, or I read it somewhere. What we're doing is adding a little more qualification to those decisions and saying, here's some data that actually supports that advice that you've heard about preferring eventual consistency. We actually show what the impact of that is versus just the advice of, oh, it's better.
I bet the majority of the systems out there are perfectly fine with eventual consistency unless you're working on a bank or like ticket booking systems. But even there, eventual consistency can work.
And the problem we run into, and this is something that my former colleague and well-known author Gregor Hope talked about many years ago when he wrote the famous article that a Starbucks does not do a two-phase commit, that almost nothing in the real world is actually transactional. So his example is Starbucks. When you go to Starbucks, you give them money, but then you go to another part of the store and you eventually get your coffee. That's eventual consistency. And the reason they don't do actual transactions is because it's really inefficient. But the problem is that a lot of business users have this transactional model in mind that, the universe is transactional because for a long time we used monolithic databases and transactions are pretty easy there. But then you move to distributed architectures and suddenly it's really difficult, just like the banking system is really difficult. If there's only one bank on earth, transactions are easy because it's one database. If there are a bunch of banks, it's a lot more complicated. Same in architecture. So the problem we run into is a lot of our users expect eventual or atomic behavior, but it's really difficult to implement for reasons like you say, concert ticketing or high scale systems or airline ticket seats, etc. So we have to find solutions to ways of allowing us to do eventual consistency, but also guarantee data integrity and
All right.
transactional behavior.
Yeah, no, that's clear. Okay, I would like to ask you about the microservices in the first place, right? The book was published in 2022, right? But since then, 3 years elapsed, and the notion of microservices as a default option kind of goes away, right? For example, Amazon published this famous article about how they switched back to the monolith and reduced cost like 10 times and so on.
So let me talk about that for just a second. This drives me crazy. Amazon has not gone back to the monolith. If you look at 99.9% of their architecture, it would still be described as microservices. What Amazon has done is what any intelligent software architect would do, is iterate on their design. And in fact, we named exactly what they did in our hard parts book. One of our chapters is about service granularity, and we talk about disintegrators, which are things that encourage you to break it down into smaller pieces, and integrators, which encourage you to bundle it back together because you've broken things down too small. And all they did was apply one of our integrators because they realized they had broken things down too granularly and it was causing latency and performance problems, so they bundled it back together, and the entire internet lost its mind because they did that. Are they not allowed to iterate on their design to make it better? Do they have to adhere to the philosophy all the way off the edge of the cliff? That is the most ridiculous thing ever. No, we have not abandoned microservices. And it's not the default option either. I think both of those are way overgeneralizations. If there is a default right now, particularly for startups, it's probably modular monoliths. I think the default right now is probably domain-driven design and architectures influenced by domain-driven design. You don't see a lot of people building old-school layered monoliths anymore. If they're building monoliths or modular monoliths, if they're building microservices, or if they're building distributed, it's probably microservices. But the last several systems that I've helped work on are what Mark and I refer to as service-based architectures, which are distributed services but a single relational database. Because there was no advantage in that architecture for splitting the data apart the way that microservices likes you to do. It was only causing headaches, and there's no reason to do it if it's a bad idea. And so we built service-based architectures because it was the more pragmatic choice for the set of trade-offs we had for that system.
Yeah, but what about the people who are saying like, hey, if you're accessing the same database from different services, that's an architecture, so and so on?
So what that means is if Sam Newman shows up at your company, you won't get all 5 stars for your microservice architecture, but you know what? You'll sleep at night. So there is no pure microservice architecture out in the world. So one of the things you have to, and this is one of the things that Mark and I stress, is it's important to understand the philosophy behind all these architectures like microservices, because that allows you to know when to bend it without breaking it. So in a layered architecture, for example, one of the questions becomes, should I ever open up one of the layers and not force messages to go through that layer? And the answer is sometimes it makes sense to do that because it's adding no value to go through that layer. But then you ask the question, what if every layer is open? You no longer have a layered architecture, you have a big ball of mud. And so if you violate that philosophy to a certain point, you've just thrown the architecture style out the window. Exactly the same for microservices. Every service should indicate its own bounded context. Sometimes that's impossibly impractical. And so sometimes it is pragmatic to have several services talk to the same database because we need transactional context. We need joins that are going to be really crazily non-performant if we try to do that at the architecture level. But you take that to the extreme, let's wire everything into the single database. You no longer have microservices, you have a service-based architecture with a single coupling point. Understanding a philosophy of the architecture doesn't mean that you always just adhere to it because Sam Newman told you to. It's understanding when you can safely break it for pragmatic reasons without throwing it out the window and actually building something like the worst case scenario is a distributed ball of mud where you start building microservices, but then you let the services talk to each other's database and et cetera, and what you built there is a mess. But that's an example of not adhering to the philosophy at all at any level. So understanding and when to break it is the pragmatic choice.
now you're ruining the whole picture. So now instead of just adhering to some principles that I heard in some corner of the internet, I need to think about my decisions.
This is one of the examples we give for granularity, actually. So what is the common advice you hear about granularity of services? It should be single purpose. That's the philosophy. Okay, great. Does that mean that all notifications are single purpose? Or all customer notifications single purpose? Or is each kind of customer notification single purpose? Because I could argue over drinks for any one of those perspectives. Philosophy is a terrible way to design architecture. You need tools. That's what we talk about in our granularity chapters. We give you tools, these integrators and disintegrators, because what you need to do, and this gets back to what is becoming the theme of this whole podcast, is a way to do iterative design in distributed architecture. I don't know of any architect who's so clever they can just look at a complex problem and the perfect distribution of services just fall out of their head. What you need to do is create a candidate and then iterate on that design. And that's what those integrators and disintegrators allow you to do. So I create these services and now let's cut these apart and disintegrate them. Oh, it's going to force me to do a transaction. I don't want to do that. So I'll do the database transaction integrator. But now let's look at the volatility disintegrator. Is one part of that more volatile than the other, but doesn't force me to do a transaction? That's iterating on your design. That's fast feedback on your design. That's exactly what you need, is a way to get feedback on your design as you're designing stuff.
Yeah, the analogy that came to my mind when I read these integrators and disintegrators is having a star, right? So you have a pressure of electromagnetic impulses that tries to rip the star apart, but at the same time you have gravity pull, and both of those forces keep the star balanced, right, in the same spot.
That's such an apt analogy that when we teach this live, we actually talk about. So one of the examples we give is, so let's say you have a customer service that has profile preferences in it, and you disintegrate it and you create a preferences and a profile service. That doesn't mean that's going to be preferences for every single thing in my system. It should just be customer preferences because I'm disintegrating it. And so we literally talk about the strong nuclear force and the weak, that strong nuclear force is the domain concept and the weak nuclear force is the disintegrator, and the weak nuclear force should not overcome the strong nuclear force. It shouldn't make you build services that don't make sense from a domain standpoint just because you're applying this tool. So we use exactly that physics analogy.
So right now, next to the computer science education, you need a degree in physics.
Well, it doesn't hurt. We also talk about architecture quantum too, so that's also leftover.
Oh yeah, that's awesome actually. Yeah, what I do, I run a business-oriented system design course. What I do to my students is I am telling them about this architecture quantum. I'm saying like, hey, one of the major like disintegrators, okay, one of the major reasons you need to push the service out is belonging to the different architecture quantum. If you here have 500,000 requests per second, and here you have literally 3, then probably that's different quantas, right? Exactly. Still waiting on this staff engineer bump? Stop just shipping tickets. Start designing systems your CFO can brag about. Business-oriented system design course cohort number 6 goes live on 23rd of July. 10 weeks, live sessions, and asynchronous personalized feedback. 70 plus alumni from Booking.com, Bolt, and Flow Health report a 50% average compensation increase within 6 months. 11 seats remaining. Apply now at websalvage.dev business-oriented system design course and use YouTube 20 promo code to get a 20% discount.
And you know, part of the reason the quantum thing came about is because my first degree was actually in physics, because my original major was in mechanical engineering before I switched over to computer science. And Rebecca Parsons, my co-author, is Dr. Rebecca Parsons. She has a PhD in computer science and did work in genetic algorithms. So that's where all the physics terms came from, along with the evolutionary biology stuff.
Okay, that's awesome. I really like that we have these physics terms in architecture that really helps to think about this stuff.
Well, Mark Richards, my co-author, is trained as an astronomer too, so.
Okay. So the only person we need is like some kind of a theoretical physicist, right?
Yep.
Last year, we faced a problem at our startup. We had to invoke a large part of our Lambda lead. We have this monolith in AWS Lambda. And we need 60% of the functionality, but being separated and act as a response to a queue event. So in your book, you say that this approach is called tactical forking, right? So let's explain to our listeners why it's tactical, what's not strategic.
So the name of tactical forking, so it's just barely tactical forking because the origin of that name is from my colleague Fausto de la Torre, who was based in Ecuador at the time. He's in Barcelona, Spain now. They have, it turns out, a whole lot of banks that have very old software systems and they can't manage to scale. And we really need to do a formal decomposition and figure out how it works and all that stuff. But that's going to take a year, and we don't have a year. We got to get something because it's starting to fall over now. So the idea of tactical forking was one of the ways to attack this problem is to say, okay, we want to shave off one part of the system into its own part and build a distributed architecture. So what tactical forking said is, okay, let's just take the repo for the entire application and clone it and give one team one half of it and the other team the other part of it. And the first team is supposed to eliminate all the code they don't need, and the other team eliminates all the code they don't need. So if it started out as one system with circle and square in it, you clone the whole thing, and then one team starts eliminating circle code, and the other team starts eliminating square code. And by the time you're done, you have two separate systems, mostly square and mostly circle. That's why it's called tactical forking, because it's a tactical way. The advantage is you can start working right away because you can clone the repo and give it to two teams and they can both start hacking away at it, and you can get functionality without doing a whole bunch of upfront analysis of what's connected to this, and if we move this, what's going to break, etc. The downside of that, though, trade-offs like everything else. The downside of that is you're not building a great foundation for the future, because when you do a tactical fork like that, there's a lot of leftover code. So if you do the square and circle thing in the square that's left, there's going to be a lot of circle code that's left in there that I can't just easily delete. That's just lurking around. And same for the other one. And it's not a great representation of that functionality. It's what I was able to carve out of what that existing system was. And so if you're just doing it in a hurry, because you need to support better scalability or responsiveness or something like that, it makes perfect sense to do that because you don't want to spend years of analysis. But if you're trying to build, the foundation for the next 20 years, I think. So the other approach that we talk about in our book is component-based decomposition, which is a much more formal pattern-based approach of analyzing how things are connected and then figuring out how to pull them apart. But that builds a better long-term foundation for building something. So a lot of it depends on the thing that I'm migrating. Is this a short-term fix or is this long-term, tactical versus strategic? So the component-based decomposition is more the strategic side and tactical forking is more the tactical side.
So the overall strategy is that we need to break up, but then you apply some tactics to do it like faster rather than proper.
Yeah, exactly. But what you end up with is not as good as if you'd spent the time to actually do a proper component-based decomposition, but that's a trade-off. I'm willing to take something that's not quite as pristine and maybe improve it on the fly. You say to yourself, whether you actually do that or not. But I mean, there's some advice there as well. Let's say that we do tactical forking and we're left over with a whole bunch of latent circle code in my square service. One of the things you might do is build a little architecture fitness function that identifies that circle code and then gradually over time ratchet down the percentage that's there. And so force the team to gradually refactor that, get rid of it to build a better foundation for the future. So there are ways to make tactical forking more strategic by following up with some good governance practices for the resulting that you split apart in a hurry.
Yeah, let's talk about architecture fitness function, because that's a topic that sparks interest in me. When I first bumped into the term, I thought, okay, that's a great idea. That's a way how to test architecture rather than functionality and see how we support non-functional requirements. But then slightly later, I realized that this architecture fitness function are just tests for non-functional requirements. If you say that modularity, extensibility, maintainability are another set of NFRs. Is that the correct mental model for that?
Well, it's not, I wouldn't say just, it is that, but it's also tests for responsiveness and scalability. So I can't write unit tests for those, have to be monitors. So chaos engineering is a great example of fitness functions that run in production because they stress production systems and make latency go up and make services disappear. All the Simeon Army stuff that Netflix created, those are all examples of fitness functions. So they are analogous to unit tests, but they are broader than unit tests. The other big difference is they are often written, almost never written.
What glanced at me is that this is observability inside, right? So the same manner you place monitors and performance tests and other stuff on your system that you need to know as fast as possible that something goes wrong, the same way you apply the same to the architecture, so that you know that if something is broken, something important is broken, then you get to act upon it right away.
Yep, observability is one of the enablers for building fitness functions like that because you need that data. One of the things that one of the other mantras we have in the architecture as code world is what data do I need and where does it live? And a lot of that lives in log files. So I want to govern that these two services never talk to one another. I can look at log files and see if they've talked to one another and build governance around that. So having observability there is one of the building blocks for a lot of the kind of checks.
It's the key to understand what's actually happening. Yeah.
And
Right.
And as I was saying, that just having observability in place doesn't make it a fitness function, but having observability in place with an alarm, an objective check, that's what turns it into a fitness function.
I would like to ask the last one question. So if you would be able to name only 3 things that modern architects should definitely do to improve their game, what they would be?
So the first is learn how to do trade-off analysis. I think your job as an architect is not find silver bullet solutions to problems, but rather how good are you at doing objective trade-off analysis when problems come up. That's where you add actual value to your organization, is because a lot of times there are no other people qualified to understand the kind of trade-offs that you do. So that's number one. The second one is work on communication. As your developer, one of the principles you try to apply to is dry, which is don't repeat yourself. As an architect, you should repeat yourself early and often to anybody that can listen, because you've got to communicate and get your vision heard across people, and collaboration is really critical. And the third one is part of the advice that we gave in the Hard Parts book is don't evangelize stuff as an architect. It's always about objective trade-offs. So always be on the lookout for, oh, that part's good, but that part has the downside. And so you actually end up setting yourself up better because all those things you evangelized end up coming back and biting you. And so if you didn't evangelize them in the first place, you never get bitten by them later on.
Yeah. All right. Sounds fantastic. Thank you very much. Thank you very much for all the time that you had with me. Thanks to our listeners. And thanks again.